happy to have Jasper to tell us about deform mirror symmetry for punctured surfaces.
Welcome also from my side. Mina asked me to provide some insight on my PhD thesis, so today I'll be taking you on a tour through deform mirror symmetry for punctured surfaces. And as a warning, this material is more than 2 years old, so the last time I worked on it is quite a while ago. It's possible there are some hiccups here and there today. Before I present the agenda, I want to say something on my vision. So what are we all intending in this? Perhaps I can put here geometry, and here I can perhaps put algebra or category theory. And where on the left side, we maybe have symplectic manifolds. On the right side, we capture those in Fukaya categories. And on the left side, if we zoom in on the specific case of punctured surfaces, well, there's also Fukaya category on the right-hand side. But there's a specific discrete way of writing down the Fukaya category in those cases. And that's called the gentle algebra. Actually, this kind of is a bit of a misnomer nowadays. Perhaps one should call it gentle category. And so today I will introduce these objects, show how one can deform them, and how to do mirror symmetry. Yeah, it was originally an adjective, like an algebra, a finite dimensional algebra is called gentle if and only if it satisfies certain homological conditions. Then all the gentle algebras were classified in terms of quiver algebras with relations, and that was back in the 80s or so. And then only much later, I think it was based on ideas from a paper of Uru, Katsakov, Yefimov, and a few others, and then worked out by my supervisor, Raf Bocklandt, that these gentle algebras, when you upgrade them with an A infinity structure, actually serve as a model, a small model for Fukaya categories of punctured surfaces. So that's the long history behind this name. And so here, filling in the punctures is now, thanks to Seidel 2001, is like a well-known thing that you want to do with surfaces. On the right-hand side, that corresponds to deforming the category, Fukaya category. So this all is a bit on the A side. I can also say something perhaps about very roughly what happens here on the B side. So yeah, perhaps you start with originally like complex manifold here, you write down coherent sheaf category here. Perhaps I directly skip a non-commutative manifold here, whatever that might mean. And I put here as a category, I write matrix factorizations category. I'll spell that out, matrix factorizations. Category MF of something in the central element. And we're here a punctured surface, kind of non-commutative punctured surface with something like potential whatever. Non-commutative punctured surface, yeah. Here corresponds to a category which I will explain. The Jacobi algebra of a quiver with a certain superpotential and a certain potential which lies in the center of this algebra. Of that, you take the matrix factorization. So this category will be on the B side for us today. Yeah, and then like deforming this, whatever that might mean for non-commutative manifolds, should basically correspond to something like deforming this superpotential and this central element. Today I think I'll be writing a lot in Q letters instead of, so Q, but you could also think H bar if that's better notation for you. I think I'll be sticking to Q. And yeah, so what's the goal? So more specifically, goal for today is start with or explain this non-commutative mirror functor of Raf Bocklandt, and then I will say how in my thesis I deformed this equivalence. The what? 2016 or 15, something like that. What stuff was in Fabian Heisen's thesis? They were later. They were that was 1 or 2 years after, because so Raf Bocklandt had first established this thing, and then I think yeah. So what Fabian Heiden did is he considered the case where the punctures are not necessarily like fully marked as one, but where you're actually allowed to have also like multiple markings on it. So these are not stops, mind you. These are the stops in this group's terminology. So Fabian Heiden did a generalization of that. In fact, yeah. Thank you, Vivek. Yeah, why is this a natural thing to do, to deform this mirror symmetry? Like deform the left-hand side and deform the right-hand side and make a functor so it's still the same. Why is that a natural thing to do? Well, if two categories are equivalent, then they have the same deformation theory, so it must be possible. On the other hand, looking for deformations of Fukaya categories and the B-sides is also a very classical thing, because mirror symmetry evolved as the equivalence of, what is it, like complex deformation theory versus symplectic deformation theory, right? And like the cohomological field structures, I think, on those spaces, those cohomology spaces, that was the first mirror symmetry that was discovered in the 80s, and only later on in the 90s, Kontsevich realized that you can actually write this in terms of categories. Recover the original mirror symmetry by going to deformation theory. So here's more detailed the agenda. One, I want to explain gentle algebras, or categories if you like. Two, their deformations. Three, mirror symmetry of Raf Bocklandt. So this functor over there. And then, well, this construction, the construction of Raf Bocklandt has one disadvantage. It's non-constructive, so it actually only proves that it exists. And only a few years later, Chouhan and Lau provide an actual construction, more conceptual explanation for why such a functor exists. And I will recapitulate this one, and after that, I will explain to you how I deformed this construction. And then applying this, or constructing.
Just a comment. I was confused what you said. Bocklandt's work actually 2011. Fabian's work in like
2011? Okay. It's specific B side. And then, so using this construction, I will most likely be following one example throughout the talk, which is on the A side, that's a 3-punctured sphere, also known as the pair of pans. Other examples are already more complicated, but still tractable by my discrete constructions over here. Yeah, so this is the plan for today. And we will dive right in with gentle algebras. The goal is to understand why or that a Fukaya category of a punctured surface can be expressed in a discrete manner or combinatorical manner, if you want. And the starting point is an orientable compact surface together with a bunch of punctures. Yeah, I don't really have a good notation for this right now. Maybe M is a set of punctures in the surface, finitely many punctures. Anyway, and choose an arc system. So that's oriented arcs. Oriented only intersect at the punctures. Arc system, by the way, it means it goes from puncture to puncture, so I'll draw this right away for you. It looks like this, for example, and such that it splits. The arc system splits sigma into polygons. So this is not an arc system. What would I have to add in order to make this a full arc system of the surface? Yeah, I have to add a bunch of arcs. Perhaps something like this. Another one here. And so perhaps this will work. You can check. The point is, after you've done this, then you can write down the gentle algebra for this. Perhaps there's a few more conditions one wants to assume. So all polygons have at least 3 corners, or equivalently edges. We allow loops, by the way. And now, yeah, go ahead. So there's no stop. Really like, goes infinitely like this. No stop. So there's infinite wrapping around these. Here's a definition. GTL sigma. Can also, or also be written GTLQ, where Q is the embedded quiver given by these arcs. Just a notational question. GTLQ is the A infinity category. Z over 2Z graded. You can upgrade it to a Z grading, but we will be doing only Z over 2Z graded with objects are the arcs of your arc system. If you want to upgrade it, you have to choose a line field. Yeah. Objects are the arcs of a arc system. Hom spaces Hom space is the span of angles from A to B at punctures. So what does it mean? If A is this arc going from some puncture to another, and B is this arc going from one puncture to another, then we can, for example, look at, yeah, we only take counterclockwise angles. Yeah, you can also do the alternative. This is counterclockwise, right? Mathematically, it's mathematically possible. Yeah. The clock is not following our mathematical coordinate system, right?
But you only take angles which are less than, you also take the
all the way around. So this would be the next larger one, and so on. I would what? Yes, exactly. So there's a whole n worth of angles. And if A and B are the same, then you also include an identity morphism. How should I draw that one? Like this. Oh yeah, and one thing I can write down directly here is the arcs have to be chosen oriented, yeah. So then this one, the degree, you can read this off, right, Vivek? What's the degree of this angle then? Even or odd? Okay, well, we're defining a Raf Fukaya category, right? And these things are oriented, these arcs, and these are intersection morphisms, kind of. There's even or odd, this morphism. Okay. So, this one is even. If the situation looked like this, these ones? Oh, well, the one full turn, everything. So if you have a line field, which either goes through or has a, yeah, you're right, so has an even Maslov index or something, then. Your question not even well defined if you haven't drawn a line. Okay. For example, if your line field was such that, like on the cylinder, that was equal standard to the third star, then everyone is even. Whereas for a different line field, you've got two different morphisms.
No, they're all the degrees always. Or no matter what. But the question is the first.
Okay. Yeah. So you get the convention. So if they point like this or both opposite, then it's odd. And the higher products I also want to give you.
And you include more objects than your chosen arc system, right? Arbitrary arcs object.
Yeah, I choose one arc system, and then I use all of those arcs as objects. So I could
How
also.
about the closed curve? You allow closed curve?
Well, they come in as soon as you take the derived category. So you take the twisted completion. And then the minimal model. And that's the Fukaya category. So, but before I state this,
Are you describing to us objects that are out of that category, or are you describing a combinatorially defined category?
I'm defining the. So I can theorem. Rapid Fukaya category. GHQ? GTL. That's a gentle algebra. Yep, exactly. So the whole fun is that you can capture this A infinity structure without doing popsicle maps or without doing a localization. And so Raf Bocklandt just guessed that structure. He said, if a structure I found is not the Fukaya category, then the world has to be wrong. And then, so he claimed this, he wrote this into this paper in 2011, and the reviewers wouldn't accept it. So he wrote to Mohammed Abu Zaid and asked Abu Zaid, can you prove this for me, that this is actually the Fukaya category? And then this is the way that Abu Zaid made a 2-page appendix where he proved exactly that this is the A infinity structure that you end up with after you take the minimum model of. So higher products, how do they work? Let's say we have a bunch of arcs. I will not draw their orientations, but I will draw you a bunch of angles. Because this is an angle. This is another angle. This is an angle. This is an angle. How many do I have here? Maybe there's alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. This ends up at, let's say, A5, and this is maybe arc A1. Then I define mu5 of this sequence is the identity on A1. Wait, I start from here, so it's identity of A5. Start here. I should draw a starting mark here. And, well, that's not the only infinity product. But, for example, if I have an outgoing arc here at the end, let's call this one beta, goes to, let's say, goes to, how should I call this arc then? B maybe? This is beta. Yeah, the orientation does not matter. Exactly. And I could also take a gamma here. What is this?
It's surprising. Why? I mean, I don't know.
Do you like it?
This looks very non-geometric. I would have thought that the A on the surface would be just.
This is literally just a Fukaya category. What's not geometric about it?
Normally to compute mu2, I do
So this is.
This is a 5 gon that computes mu 5. It goes by identity. I would have thought that a 5 gon should compute mu 4. And definitely not.
One end of the 5 gon is activity.
Yeah. So you would have to imagine that.
So there's something unusual happens in the right. Yeah, where's my 6th side?
It's like it doesn't perturb the first and last one. A5 is happening twice. And then the self-intersection of A5
It's like here.
No, but in general, right? If I just give you on a plane, forget about my. If I have a triangle, right? On a plane, which is straight line, with some suitable orientation, it's actually going to give me a mu 2. And a 5 on a plane is absolutely going to give me a mu 4. So what's happening here?
You've drawn a 6 gon, you haven't drawn it. But an A5 should be two different pieces.
Yeah, it's
And then an A5 is like X.
like here.
All right. Actually, you need to survey 5. Okay.
Yeah. So that's exactly what is kind of the non-trivial part of showing that this is the Fukaya category. Right. And so these are the higher products mu greater or equal to 3 and the product mu 2 is as follows.
I say, and beta is some wrapping applies also 5, is that? In the other guys that are.
Here?
Yeah. So you wrote 3 new 5 products. The beta and gamma correspond to extra wrapping in that corners.
Just a morphism. So it's just a longer morphism. Like there are multiple arcs incident at one puncture, and this is just beta alpha 5 is just a longer morphism. So it goes outside of the immersed disk. The higher products are given by immersed disks.
Can you show like how beta is? No, I don't understand.
Where's the second line?
Well,
Can you go just draw one polygon for the second mu 5? What does it look like? It still has to be a polygon. It has to be close.
good. Yeah, I can try now. I pass. Better try later on. So you want to see where the 6 gon is with this long angle that results in this thing.
I mean, maybe
It's like perhaps something like this, something like.
Okay.
Yeah. So you can. Okay. Check.
So for this higher product, what kind of disk do you count?
Immersed disks. Yeah, so there's a discrete notion of immersed disks. It's exactly the same notion as in Haydn-Katsarkov-Kontsevich. And all immersed disks in most literal sense means a mapping from abstract polygon to your surface such that the polygon edges are mapped to the arcs. And the corners are mapped to the corners. Yeah, and such that no punctures are covered. No punctures in the inside. Yeah, so immersed disks.
What is immersed
Without punctures. Yeah. So if you were to restrict to just embedded disks, you would not get an A infinity category, because the A infinity relations have to satisfy the A infinity products have to satisfy the A infinity rules. So it means something like if you keep gluing things. What is an immersed disk? Yeah. So did I answer it already with the definition or? Same picture with what?
You had told me that was an embedded disk.
Just explain what's immersed about that.
Oh,
Well, it should fold on itself, right? But just square.
Immersed. This one doesn't fold. Immersed just means it's allowed to fold. It just means it's allowed to fold. For example, that's why I was drawing this picture. So for example, look here. Let's say we have this marked surface, right? This punctured surface. A lot of arcs here. I've drawn 3 triangles incident at this puncture. And now I will draw you as, how did I say 3? 6?
I see 6, yeah.
Sorry. I'm too tired or something. Okay.
It's all right, 3 or 6, we can count.
I'm having too much fun. Okay.
Now I'm okay.
So what I will draw for you is, this is not an immersed disk. Because there's a puncture in the middle. Okay. But if I start here and I end here and then I go back, that's an immersed disk. So 1, 2, 3, 4, 5, 6, 7, 8. But yeah, so geometrically, exactly this picture. I can keep going. I can add some more angles. And only after that, go back to the beginning.
Is this only allowed to turn around at the corner, or is it allowed to turn around in the middle of the edge as well?
No. Only, so the corners have to go to the corner, so it's only allowed to happen at the corners. I can build larger and larger parking garage style disks this way. You see.
So the data in the word disk is just each corner in the main disk, which corner, which puncture.
Yeah, and a filling, because a priori it's not clear that if you only prescribe the boundary that there's one specific filling, right?
No,
yeah.
the most one.
You need what?
How can it be more than one?
Do you know the Bennekamp curve? That's immersed curve, which bounds 2 different disks. We'll figure it out after the talk.
Well, as multi-cover, right? You got the slip example.
I don't understand. If you say corners go to corners, edges go to edges, I prescribe 2 consecutive corners, where they go. You prohibit by God, because it's going to be both one edge.
How many disks?
I'm happy if you can prove there's only at most one. I'm happy. That's also okay. Rina. Okay. We will go on. So here's a product mu2. And as you can guess, if I have a situation like the following, like here's an angle. Here's another angle. And the mu2 of alpha comma beta is 0. So if there's no sensible way of combining and concatenating them, that's 0. So this should explain all the higher structure on this. And I already gave you this important theorem here. I gave you why these gentle categories are called the way they are. Yeah. Yeah, like, you see.
What if there's a third puncture?
But he assumes that it's not.
Even if there is, it's going to say
They're inside one polygon. Like that's the. That's the. What's the question? 0.
That's still 0. Right?
Yeah.
So it's not because they got it. Oh, because that means it's 0. Okay.
Okay. Yeah.
In your theorem, the sigma any boundary.
Where what? Here?
Yeah.
Only punctures. Yeah. So, yeah. Sigma is for us always punctured surface. Yeah. Sigma is well, sigma is a compact surface, and then you remove points. Thank you, Vivek. Okay, so deformations of gentle algebra. Go. See that Seidel's relative Fukaya category is one deformation of GTL sigma, but there are more. More as well. And the idea there's a puncture in the middle, 4 punctures on the corners. And let's call this puncture Q. And I'll draw you 4 angles. Then I will define note that there is a Q now here. Or just deform, whatever. The idea is basically, right, this is Q times the identity of where I started. So this is arc A. It's Q times bit A, and so on. I just modify all the A infinity rules so that they count how often they cover punctures like this. Yeah. Yeah, exactly. So if it does this, if it's very large disk and it comes back to Q twice or 3 times, it will be Q to the 2, Q to the 3, so on. So that's just a rough idea, but how to make that rigorous and what other deformations, how can you do? Perhaps I should start by giving you a reminder of what is a curved A infinity deformation, so that everything I will be writing after that is well defined. So, recall. Recall, let's say C. Let's C be an A infinity category.
Suppose your target surface is a punctured sphere. Are there still more deformations?
The target space is a punctured sphere.
In this case, when sigma is a sphere, the punctures, are there still more deformations than just the relative?
Yeah, just one deformation is of course never enough because the Maurer-Katan element is so huge.
No, you won't see a different parameter for each puncture.
Yeah, that's already better, but then still you will see, as I will explain, that that's not enough.
Let me tell you, let me explain. So,
Let me maybe make it clear.
okay.
So such that is R linear, R multilinear, linear. Its zeroth term, so after dividing out the maximum ideal, is the original non-deformed product, right, like this, and of degree 2 minus k as always. Mina, will I need another talk, like in 2 weeks, to get to the end?
Just go slowly and try to think.
And we allow curvature, but only infinitesimal curvature. Because as I said, we want all the zeroth terms to reduce to the original structure. So if we start from a category without curvature, we want that the deformed thing reduces back to 0. So only infinitesimal curvature. So I can perhaps make this explicit by saying that the curvature is a multiple of elements in the maxima ideal. So yes, the classical example, this, or call it Q or whatever. Such that, here's another such that the curved infinity relations hold. And if you haven't seen them, they're kind of the same as the original A infinity relations, only that we allow the curvature to be there. So one also counts as an insertion. As you already see, so the curvature lies now in the kernel of this mu1, but mu1 is not a differential anymore. Yeah, so you deformed something which was nice category as a differential to something that is not even a differential anymore. We think this is super badly behaved in a homological way, but tell me. Where? Mu2 of mu, which one? Mu2 of mu1 of something? Like, and what here? Like this? Like this? So, why is this what?
Why are we calling this curve?
Yeah, so this is for historical reasons called curvature. Yeah, there's a reason, right? You can explain it, Vivek. I cannot make this up right out of my mind. So why is curvature the right name for this?
If you're going to explain why on the B side this is right,
What on the B? What?
but then you're going to explain why the B side is curvature. There's no first category is not coherent, not category.
Yeah.
What's true is that your first category, that's how you discover a non-curved category. And that further correction, that one will be
A what?
Second term, I think you have the three.
Did I forget it? Did I forget the term?
Yeah, what would you have the mu 3 as well? Mu 3 was 2, mu 0.
Oh no, just like with a standard infinity relation, you're only supposed to have one mu in the middle. Yeah, so that it stays quadratic. Remember, infinity relations are quadratic relations. You're supposed to have one outer and one inner precisely. Because it's the completed tensor product. It's completed in the m-adic topology. So for example, if you take any vector space algebra, any vector space A, and you just tensor with this thing, you get something else than this. It's not the same. In order to achieve this, you have to put this. So that's just to make these, to make this make this work in the classical way. Classical and predictable and limit compatible way. It's just good, very good question. So remark. Remark. There is a DG Lie algebra that captures the deformation theory of infinity category C. Given by this complex, which you know as the Hochschild chain complex. And raise your hand if you knew that this is also a DGLA, if you know that this, beyond having a differential, also has Gerstenhaber product. Raise your hand. No bracket. Yeah, a few, that's very good. So, what does this look like? So remember, so eta nu is defined as all possible insertions of nu into eta. And this is just an auxiliary definition because what we do is we put this. Yeah, I cannot remember the signs, unfortunately, guys. I'll put it like this. And d eta is mu. D of mu is mu commuting with eta, where mu is the product of C viewed as an element of this large chain complex. And the grading of this chain complex is also not by the length of these tensor terms. That would be how it's classically for associative algebras. But the grading is by the inherent grading of these Hom spaces. Z over 2Z grade or Z grade. Inherent grading of these Hom spaces and therefore also this large Hom. So that's a remark. And so deformations of C over R are the same thing as Maurer-Cartan elements of HC over R. You can convince yourself relatively easily of that. Just write the A infinity relations as this, and then use that mu times mu is already 0, and then you get exactly the Maurer-Cartan equation. Mu? Mu is the A infinity product, the non-deformed A infinity product on C. Now, yeah, so this is kind of a nice deformation theory. So once you have equivalence of two categories, then their DGLAs are also equivalent, which means that in theory, whenever I deform one category, there must be a corresponding deformation for the other category. It can just be ridiculously hard to determine that other deformation. And that Choung-Lau construction, about which I'll be talking later, gives you one tool to get more grip on this, how to transfer deformation from one set to the other. So I should just mention a few. Yeah, we start with a deformation of a gentle algebra, and we want to push that to a deformation of the matrix factorizations. Exactly, yeah. So here are a few stuff which I proved. So you might think if you have a infinitesimally curved infinity deformation that is homologically very badly behaved, well, that's in some sense true. But on the other hand, remember, that C and its twisted completion, there's like complex of objects in C. C and its twisted completion have the same DGLA. Not exactly the same, of course, inclusion, restriction, and quasi-isomorph. So they have the same deformation theory. So if I deform C to CQ, then there must be a deformation of that category, which corresponds to this. And I constructed this one, not that hard. Yeah, it's also curved and such, just like follows ordinary lines. One thing that's way harder to do is a minimal model HC. Perhaps I remove the brackets. HC, minimal model of C, also has the same DGLA as this. So there must be some notion, some deformation. Perhaps this is the better way to write it, but I define this. So I say must be a notion of taking a minimal model of deformed A infinity category. So this is a deformation of this guy, precisely the one which corresponds to here.
So we start with the uniform theory, then you say an infinitesimal deformation is curvature, and you're not completing it, integrating into a finite deformation, which then gives you a proper infinity category.
Yeah, I'm completely, yeah. So in my opinion, for whenever we're doing infinitesimal deformations, it has been a failed development in the literature to try to always get back to an infinity category. If we do only infinitesimal deformations, so only over formal rings, then it's perfectly valid to stay curved. Yeah, correct. So the mu1 on
you're not guaranteed to be able to complete it to a finite deformation, or you in general, right?
what is a finite deformation?
Well, so you get an honest category.
Yeah, I see.
On curve.
Yeah, I'm not doing anything that direction. Yeah, this is correct. I forgot to say that perhaps, yeah. But the mu1 on gentle algebras are already minimal model. Their mu1 is 0. If I forgot to say this. Okay. So I proved some stuff. I proved that these things exist, but well, in theory, this is trivial. But I also described how to compute them explicitly. That's okay. I will give you the precise statements after that. Is that okay? Good.
Jasper, do you want like a 10-minute break? Would it help?
Yes, okay. Let's do it.
If you'd like.
Yeah, why not? Thanks.
It's great.
I'll be back in a minute. Welcome back, everyone. So as I understood, there's kind of interest to take things a bit deeper, and perhaps we'll have a second talk at some other point. I will see how far we can get. Perhaps at the end, highlight a bit of those results. But for now, I'll try to get things a bit deeper. So let's see in infinity category and CQ a deformation. We're always talking formal, so it's always over local C algebras. Then there exists one, the deformation. I call it this way. Of HC. Such that now there are various ways of expressing what I will be telling you. One way to say it is that such that there exists a same context, so curved infinity functor such that FQ reduces to given infinity functor F. So we start with a quasi-isomorphism. I'm saying there is one deformation of that category which does the same thing that we expect from a minimal model, just this time for CQ. So this like saying that HCQ is a minimal model for CQ. Only that it's allowed to have. It's a deformation of this this guy, so in particular, it's allowed to have infinitesimal curvature. Yeah, deformation is always curved. Yeah, deformation in my talk always refers to that definition which I had above, always allowed to have infinitesimal curvature. Curvature is really not a pain here. Second, same things hold for twisted completion. Yeah, I could make things more explicit, but yeah, such exists curved. Of course, only allowed to be infinitesimally curved, but that already follows from what I'm going to say below. So, Functor. In particular, there exists a notion of a draft category of C. Now you might wonder, given that this all follows purely from the equivalence of DGLAs, is there actually something interesting about this? The answer is yes, because the interesting part of the theorem is still missing, namely that you can explicitly construct these things. No, the statement is that the homotopy transfer theorem does not work there. You have to use a modified homotopy transfer theorem, and so I did that. I defined a deformed version of the homotopy transfer theorem. The first step you have to do is optimize the curvature, because the curvature has a lot of wrong features. They're not compatible with mu1. The first is a curvature optimization. That process is all very, very complicated because in every iteration, it's an iterative process. And every step of that iteration, you need to compute a new splitting of the deformed Hum spaces of your category. But after you've achieved step 1, comes step 2. You have achieved a final kind of optimized splitting of your deformed Hum spaces. And on that one, you can apply a construction with trees, similar to the classical one, but with additional trees, of course, where you now insert these curvatures and so on. And that one gives you a deformed structure. Of course, the deformed structure is then defined on one of the 3 components of your Hum space that was being split. Remember, there's Hum space into cohomology, image, and remaining term. Yeah, so on the cohomology, but the cohomology is not immediately cohomology of the original category tensor, the ring. It's actually a deformation of that. So you have to bend things back to HC tensor R in order to be an actual deformation in the strict sense of that category. So it's a whole 3-step process, which I worked out in one paper.
A lot of hard work. You constructed a homotopy transfer theorem
Yes, that's very correct. Yeah, exactly. Did you say, yeah? Yeah, that's the, exactly. So I should say here, so end of the theorem, so part 2 of the theorem is, and these can be constructed explicitly. That was also necessary for this large project because, as I will explain to you later, this Chohung-Lau construction demands from us that we compute a large part of a derived category, like the infinity products of a derived category. And if we want to deform that, we'll have to compute the deformed A-infinity products on the deformed derived category. So deformed and derived. And that's why I needed this stuff. So this was all general deformation theory. I think we're still, are we in chapter 2? Call this 2a. Defos of the specific thing here. Deformations of gentle algebras of surfaces. What do you always do first when you want to get a vague grip on deformations? You compute Hochschild cohomology. It's often ridiculously complicated and took me a lot of time and so on. I started at the beginning of my PhD. I ended at the end. Now, so this computation was an intensive thing where it was never clear, should we continue this till the end or not? But I did that. And what's the result? The result is that for each of your punctures, so let's say n is the number of punctures, you get a lot of contribution. How much contribution do you get? I'll write this here. I is 1 to n. This is true as just super vector space, even odd. But we were able to say much more. So this was just for our orientation, yeah, you know. And I gave explicit representatives of bases, these basis elements. So and yeah, I should so I can say more. So if so. Let's see. Which one? This one? Yeah, just means all polynomials in that variable with degree greater than equal to 1. It's just like there are no actual zero terms. The zero terms are together with a bunch of other terms, like we call them sporadic classes. They are in here. Yeah. So the L infinity structure is formal. And so yeah, the differential on this is 0, of course, because we've taken cohomology. And the bracket you can I'm writing this by heart. It's something like this, right? So it's suggestively that we wrote things this way. Oh yeah, and then what is it? Perhaps roughly like this. There's more to it. Yeah, no, I mean, so thanks for the question. So I meant this one just as a function in odd, and this just a function, like in some c xi greater equal 1. I was just giving some examples. So we gave the whole list of the L infinity structure, and we also computed the cup product, which is another separate gadget. Computed the cup product. Oh no. Thanks. Should be like this, right?
So what's the geometry of these deformations? I would have thought that once we decide to fill in a puncture, it should disappear. But this sounds like, or at least there should be a way of filling in a puncture, so just by erasing. Is there such a thing?
Yeah. So exactly. So intuition. This element corresponds to filling in puncture number I. Puncture numero I. xi squared corresponds to what? Vivek. Yeah, so it's HH1 actually. HH2 is if you have associative algebras and you use a shifted, like a non-shifted grading.
So your grading is shifted.
This grading is the modern grading. The one you're talking about is the one which Gerstenhaber used 80 years ago for associative algebras. Remember an associative algebra, and then you shift that associative algebra 1, then you have an infinite algebra. What?
We have no actual disagreement. We have a different grade.
Is it what?
Different grading.
Yeah, so the odd ones are the actual, are the. Yeah, and they are, yeah. So we are working Z over 2Z graded, so that's why they are odd. How do you think?
I'm more basic. So I thought deformation, never mind whether it's even or odd. I thought only one of those two things.
Yes, those. But Hochschild cohomology also has even terms, right? They are not deformations in any strict sense, but they're still part of the DGLA or the minimal L infinity structure. Yeah. And this result this is new, I mean, for our computation, but it was by no means unexpected because, yeah, this is something like symplectic cohomology, right? So it's something you expect. And it's also like similar computation had already been done on the B side, with the difference that on the B side, it was done on a slightly larger category. So it was kind of funny that that we recovered exactly this thing. It's really, yeah. The whole vector space, this is just given odd degree. Yeah, they don't have an individual degree. No, they don't have individual degrees. Yeah, it's just I take some vector space, I put this in degree 0, and some vector space which I put in degree 1. Yeah. Very good, thank you. So this one actually corresponds to filling in puncture numero I, but as an orbifold point.
You're saying one can consider the level
Yeah, exactly. Formality is interesting for plenty of reasons. First, because if you have formality, then the structure is kind of easy. But second, if you know that something is formal, if you know that something is formal, you have determined the entire L infinity algebra. And this means that if you want to compare that L infinity algebra to something else, to some other L infinity algebra, the deformation theory of some other category, then you know what to look for. You always, well, formality in a sense, formality is not that essential. What is essential is that you have the minimal model. What's essential is that you have the L infinity structure on Hochschild cohomology. So that was very satisfying.
why do you call it intuition? That corresponds literally true.
Yeah, good. Yeah, you want to give this a name? So I should quote Vivek or Shilganatra, Seidel. Okay, great. So the whole point of this work is that this deformation of mirror symmetry had never been done for punctured surfaces. And even though a lot of these things were like expected in general for any higher dimensional Fukaya categories, seeing that this works out for punctured surfaces required already crucial technical effort, and we made it true. So now I want to give you some deformations which you might not have seen yet. So I will call this a theorem instead of a definition.
There's some kind of global orbifold, right? There's no global constraints about you can choose this orbifold kind of filling in every puncture separately.
Yeah, exactly. So that's what we're going to do now in this theorem. So for every, I will call this a deformation datum, puncture, datum, whatever, datum R in M hat tensor this HH odd. So we construct explicit deformation, which we call this way. And so the theorem is kind of we constructed it and it satisfies the curved infinity relations. And its curvature is what? If you pick an arc. Pick an arc like this. And let's say let's give this example. If R is this ring, and R is just Q times xi, then at this puncture numero I will attach one full turn as a curvature. So Q times one turn around that puncture I It's the curvature of that arc. Every arc which bounds, which neighbors this puncture will obtain its curvature. So its curvature is, example is, I could also write down a few more general formula. One thing I will write for you more generally is its higher products.
I see, so every object that ends on this function has this curvature.
Yeah, exactly. So its higher products. Our products are as follows. Let's have an orbigon disk. We defined a precise notion of that. An orbigon disk. See, so which let's say it goes over this puncture numeral I with orbigon index K. Puncture number. This puncture and here another puncture J. What should I call it? JL and whatever. A lot of punctures. Then mu of those angles will pick up these R terms. The R is the term, perhaps I should write R IK times xi to the k. So you pick up an R term for every punctures which your disk covers. That's I, K, J, L, whatever amount of R's times what you would ordinarily get as output if those punctures were not there. Yeah. So times whatever identity of some arc or the beta or gamma, whatever. So we construct explicit deformations.
Sorry, can you say this again? So
yeah.
What is the deformation of this? What are the R's?
The R's. R is the R's are defined here.
Oh, okay.
Sorry. So we pick a deformation datum, and I will just write it out as this. And now I define that for every disk which has a K orbifold point at puncture I and an L orbifold point at puncture J, and we could, and perhaps again at some puncture A, but with another index or the same index, we multiply up all those R's which appear in that disk, and then times what the ordinary rules tell us, like identity or that beta angle if we go outside.
I see. So
we define
if
it.
you weren't for the punctures, you would have this. If we just erase the punctures, you would have that new product.
Exactly.
Element. If the punctures are there, it's still there, just with this coefficient. They're coming from the filling in. And if you set a coefficient to zero, meaning the punctures aren't filled in, then it's zero.
Yeah, then it's zero unless there's a disk, unless you have a disk without punctures in the middle. Okay. Exactly. Yeah. So for those ordinary disks without punctures, everything stays the same, and those disks, and there are few disks, they will start picking up terms, infinitesimal terms. Okay. That content will come here. So theorem.
But he gives an explicit definition.
My point is that the previous theorem was explicit almost only transfer theorem. Then he said that definitions are obstructed by the formality. I'll tell you how to write this one. Is that more or less correct?
The formality thing. Then no, yeah, very good one. I was thinking a long time that I wanted to do the following thing. So for a long time, let's say I think the third year of my PhD, I was trying to do the following. Raf Bocklandt gave me this functor, of which there was no explicit construction. I said, well, okay, if there's no explicit construction of this, we have zero chance of transforming deformation from one side to the other, unless we go to Morat-Catin elements and use that these need to be equivalent. Oh yeah, by the way, this needs to be a dual dimer. I will explain that later. I'm just giving now a preview, yeah, for UVVAC. So a preview for UVVAC is what I was trying to do in the third year of my PhD is we have given this functor, even though it's not explicit, then there must be an isomorphism of L infinity algebras. And because they're both formal, and perhaps we can guess a few more properties like grading and such, yeah, then we should be able to pin down this isomorphism. Yeah, and naturally there are also quasi-isomorphisms here because this is just the cohomology of this one. Yeah? So we are actually, what we want ultimately is this one. Yeah? We want to be able to transfer actual Morat-Catin elements. Yeah? And my trick, which was pursuing at that time, was let's try to pass this to cohomology instead. So this map which we want, which naturally exists, must induce something on cohomology. Yeah. It will be respect some grading with respect to those xi's and such. So I was saying, well, if we find that it's formal, if we determine the entire L infinity structure, maybe we can actually pin down that once we write down both these things in terms of this standard formula over there, then this should be the identity. Yeah? And these things we have chosen explicitly, perhaps, and then once we've proved that this goes down to the identity, then the only thing to do is to take Morat-Catin element here, see what it goes to here, then this the identity, so it remains the same here, and go back here. And then we've transferred a deformation through mirror symmetry. Now, the reason this is a preview and not the topic of today's talk is because this failed. Not because it's impossible, but because I was never able to construct this isomorphism explicitly. And even if I had achieved that, a few things were lacking perhaps to pinning down that this was the identity. But I was working hard on that. I was comparing these gradings. Basically, what you're doing here is you're computing automorphisms of that L infinity algebra. I was spending a month or more on computing all possible automorphisms of that L infinity algebra. See? Just in order to be able to pin down that it must be the identity, that there's no other graded automorphisms of this L infinity algebra. Yeah. But ultimately, as I said, this failed because this one was too hard to write down. And then my supervisor came in and said, well, Jasper, I found this paper of Cho, Hong, and Lau. And they make an explicit functor. Yeah. And perhaps if you succeed, Jasper, in deforming their construction, you can write down a deformed functor, a deformed way to arriving at the right-hand side, naturally. And I did that, and that worked out. And so that's the matter of the rest of it. It's a combination of this. This part ended. This is a calculation. It ended up playing no strict role for this transfer of mirror symmetry because we were ultimately their construction requires more or less that you start with one with one specific thing, and you could not want to deform everything at once. Do it. This is calculation, correct? So this is calculation. This theorem is a construction. Now comes a theorem. This one? Is whether that it relies on a grading argument. And Yeah, exactly. So the bracket you can compute that's just a 2 tree, right? And the higher trees you can prove with a grading argument that they're 0.
The one you call a construction, what I'm confused about or trying to understand is it a construction? So you already described one construction. You described all that it was not going to transfer over. My question is this construction a formal consequence of the homotopy transfer plus the formality? Plus the fact that you look at your bracket, everything's in it.
Yeah, so I think it would be a consequence if, so recall that I've already written this down here. I'm just writing it the same thing horizontally again. Here's the difference. Cohomology, not cohomology. Yeah, there is a quasi-isomorphism. Yeah, and if you know this quasi-isomorphism, then you can push forward Marokatan elements from one to the other. But and then gives you this. Yeah, you push this element, and you arrive at that deformation. Fine. However, in order to do that, you first have to construct that one, and ultimately I ended up throwing that out of my thesis, even though the construction that one is a bit more general version of this theorem, indeed. Yeah, that should explain it. So if I had written down this, I would have essentially already done this. It's whether you do this one or this one is more or less the same amount of work. Yeah. Here goes the theorem up to gauge equivalence. Every deformation recall we are z over 2 z graded, just so you don't wonder why there's so many deformations. Every deformation of GTL sigma is of the form GTL R sigma for some R. And this one would follow also from having this one. Another way to derive this, which I ultimately followed, was to apply Schlesinger's theorem. You want to see the proof? You believe it? Okay, yeah. Basically, the idea is that this GTL whatever forms a deformation functor itself. I can, for every element in here, I can make up such a thing. So this family of deformations is a deformation functor. And so there is a map from kind of Hochschild cohomology to this deformation functor. And because it's an isomorphism on first level, it is an isomorphism everywhere. So all deformations are given by GTLs of such elements. Does this board go up? This one. Thank you. Sorry, so I wrote, did I write on the board which does not go up? What would you prefer? I write on another board here, or I skip to that one for the moment. I can erase this? Or go like this?
Actually, why XI and XJ why does all the information have that form? There's something going on. Why XI, XJ?
Yeah, good one. So question, why are there no defos of the form xi xj.
Yeah.
So that's the fucking homology. So the product is the fucking homology system. The xi, xj would mean that a cylinder going from one of these to another one. That cylinder is the surface function.
Thank you. Another specific way in which one can look at this is that such a deformation should somehow have curvature arguably. What curvature would it be having? At such a puncture, it would perhaps have like something, one turn around that puncture, but that other puncture is somewhere else.
Yeah.
So these are kind of independent of each other, and it's more that xi plus xj. Yeah, it's not a product.
Okay, another question we go. Suppose I start with a cylinder, P1 with 2 mark points. Can I glue the two ends together?
These together to get a torus. Are you thinking of something like QL1 and here minus QL2 as like the curvatures or something like that?
Yeah.
I'm trying to guess. Yeah, so yeah, I see. So if you add up these two curvatures, like you would end up with zero curvature, and that's what you expect from P1 or?
No, I was saying, okay, suppose I start with P1, and suppose I want to just glue in two independent disks, and I go back to P1.
Independent disks.
Yeah. But suppose I want to glue the two ends together.
No, I see. Okay. Yeah, apparently the only deformations are given by gluing on individual disks or orbifold points. Yeah. Yeah. Mina, I stop when?
It's up to you.
Okay. I will stop at the latest at 10 past 4. And as we said, we can do more talk later on. So these are all deformations. And so that's more than only those which Seidel had in mind, clearly. Oh yeah, and so here. This is the computation which took me, if you condense it very much, it's like 30 pages. If you write it out so that's human legible, it's like 100 pages. It's a subcategory. So I proved that for this specific choice of base ring, namely one deformation parameter for every puncture, and this specific choice of R, so that just like Seidel would be doing it for every time you encounter some certain puncture, you multiply it by that puncture, that the deformed derived category using my homological perturbation lemma, is indeed isomorphic to the relative Raf Fukaya category. Why what? Why would this prove anything at all? Because that's not clear a priori. Well, okay, I can explain it. So what do we know? So why? So what would we know without this? What do we know without this? We know from Abu Zaid that this thing is the Raf Fukaya category. What? Where? Yeah, that's minimal model. Yeah, I'm writing quasi-equivalences here, or quasi-isomorphism here anyway, so I could also remove the... Yeah, you can, if you want, I can... If I only put the right notion of isomorphism, I can remove all these symbols. Yeah. So this is the same. So that we know. But once we deform, there's nothing guaranteed anymore. That's true. Yeah, it's if we knew, I have so once. Yeah, exactly. Yeah. So if we knew this guy, then kind of we would be able to see that that deformation which we're doing here right now corresponds to. Oh yeah, okay, that's also okay. If we the same diagram, where is it? The same diagram holds there. So if we knew that a certain element of a symplectic cohomology corresponds to precisely this deformation.
So you're saying if I knew this, so I know that symplectic cohomology of this kind of category is about the same formula. If I knew that Shields isomorphism is the identity,
yeah,
then I could skip the rest.
So let's make precise what Shields isomorphism should. What we mean by Shields isomorphism, but yeah, that's basically the argumentation. So if we knew that this is the identity, while this is something known, in particular, the relative Fukaya category is a Moragata element in here. That's the whole joy of the story. And this is
which one?
yeah, it's about finding the specific R which gives this thing. Here?
Anywhere on the left. So my understanding, anywhere on the left of your diagram, you know which element gives the correct definition.
So we know this map. Let's say we know this map.
Anywhere on the right of your diagram, you know which element gives the desired definition.
So this is.
No.
Yeah. So if we.
Whatever. You can tell me anything you ever wanted to know about cohomology, all terms about it, anything direct calculation whatsoever, right? I mean,
that's also true.
If you were having this cohomology, and it wouldn't have been.
No, there's content here. The content is a partial cohomology element is a certain particular element. That's what he's asserting. He's asserting that a partial cohomology element, there's two questions. One question is it enough to know this partial cohomology element? It's also higher order stuff, so that's one question.
Yeah, so Hochschild, yeah, good.
Never mind that question.
Yeah.
More basic question. Do I have give me a relative category. We all know what that element is. One copy of each of the three. So then she has an isomorphism, which in this case is subject homology, functional homology.
Yeah.
That's sometimes called what curves, but we do it.
Yeah, okay. Yeah, this side.
And so on that side, I believe that on that side, you know, for all three of those things, which element gives you the deformation. And then, the thing that confuses me is that if you also knew, maybe if you're saying, if you also knew isomorphism, optional homology is a general thing, and optional homology is right category, if you knew that is the kind of obvious identification in this formula, corresponding formula in symplectic homology, then would I, from that, be able to skip the rest?
Yeah. So if you know that for this given, and if you will this given, that this map induced from Abu Zaid's map is the identity, then yes, you can skip the 100 pages. Yeah, that's exactly the point. And because I was not able to prove that this is the identity, and for given this and this, I had to do those 100 pages. And it's also one more thing I wanted to let you know. Namely, I believe that this thing did not exist before. Tell me. What? Relative wrapped did not exist before, right? So
If you can use some close-string computation that will bypass doing deformations that are finite, then there is an easier way to do this project than trying to Jasper and I, trying to find the conversion. We know it in complement of something. You probably know everything about it.
Point of whatever you discuss. If you do not have the analog of symplectic homology in that situation, so the sheaves isomorphism between symplectic homology of something and optional homology of your category does not exist for the show world. Because of that, you would not be able to skip.
Does it even make sense in the show?
I mean, who knows? I mean, I don't know. I don't know what you can substitute. Surely there's something.
you're happy with it? Great. So essentially, what I did was essentially construct a relative wrapped Fukaya, which has also not existed before. Only for surfaces. Yeah. Constructing this thing, I have essentially constructed a relative wrapped Fukaya.
But you have a definition of relative wrap?
No. So it's kind of
So you prove that this is isomorphism on the top.
yeah, exactly. On the subcategory of zigzag Lagrangians.
And then you say by definition this is
Yeah.
And the zigzag the guys who go
What are zigzag zigzag means you zigzag, you go left and right. So small angles here, you see. As one can give a more instructive example. And then you connect, you take the Lagrangians, which is. Yeah, exactly. So. And yeah, and by the way, so one has to make restrictions on what sigma is here. Also, I did not explain. Sigma is supposed to be a dimer, only then it works. Consistent dimer model. Yeah, and so I'm supposed to wrap up. Tell me, Mina. What's a dimer?
We'll come. Some comments about sigma and dimer models.
Yeah. Well, a dimer model.
I know what's a dimer.
Is it? Well, yeah. Perhaps you know one definition. The other I can illuminate you. A dimer model. You know that this stuff comes from Amihai Anani,
well,
probably.
One of the
you. Yeah, I guess so. Yeah, I only learned from Amihai that he was behind that, so in one way or another. A dimer model is a punctured surface in which all polygons, all the arcs in the polygons are oriented either positively or negatively. So nothing mixed. So this one is this way around, this one this way around. Why is it then called? Why is this thing called a dimer model? Because this gives you these edges gives you make this bipartite, right? So every clockwise thing only bounds to anti-clockwise polygons.
So where do dimer models enter your story?
Because for most of my thesis, I had to require that sigma is a dimer model. It's just a specific type of punctured surface and arc system. So dimer model. And with this, I want to close my talk today. I'll just give the highlight sentence of what we'll be doing with this. So once we've picked this very specific deformation, I will show you next time, whenever that is, how to push that to the B side. And that's a very non-obvious thing because, as I said, Bocklandt was not able, he was able to show that there's a functor between A side and B side, but not able to make it explicit. And in particular, it was so hard to deform. But then Cho Hong Lau came in and they said, well, we can do this. It's actually some kind of a version of Koszul duality with curvature, something like that. And next time I'm going to show you how this version of Koszul duality works and how I deformed that thing and then was able to pull through, apply that to this case, and get a deformed B side.